of work on electrochemistry, on oxidations and all this. Also on ab initio thermodynamics and multiscale modeling related to the topics of this conference. And today she will talk about insights into processes at solid-liquid interfaces from ab initio molecular dynamic simulation. Okay, so Mira, the floor is yours.
Thank you very much for the nice introduction, and thank you very much to all the organizers for inviting me and giving me the opportunity to present our work at this very interesting conference, which I enjoyed tremendously so far. So I hope that I can add a little bit to it by showing us our work on solid-liquid interfaces. And I don't have to convince you that solid-liquid interfaces are ubiquitous and are at the heart of many processes we are interested in. We've heard examples of various problems where solid-liquid interfaces play a role. This is only a small part of them. What we want to understand, when we want to understand these processes, we need to think also about multiscale modeling. We heard about this. We need also to think that when a certain device is produced at the laboratory scale, we need to think about upscaling. But these are problems I'm not so concerned with. I'm more interested in the fundamentals of the underlying processes, and while we see something like corrosion on the macroscopic scale, of course, where it starts is at the atomic scale. And the atomic scales, this is here a cartoon view, is not simple. And we've heard throughout these conferences a lot of different talks about approaches and techniques which help us to learn something about this atomic scale and the processes that are going on there. What you can see already from this kind of cartoon picture is that, of course, we have to be concerned with very many different materials classes. Obviously, there is water, which in terms of modeling will put will present different challenges as compared to the modeling of an oxide or a metal. We have to think in particularly about statistics when we think about water, and we can either try to use molecular dynamic simulations or we can try to describe water in some kind of averaged way or a continuum modeling, as we also heard about, for example, by using some vast sol was mentioned several times throughout this conference. When we think about, of course, oxides and metals, so solids, usually we kind of deal from the theoretical modeling with more idealized systems and don't care so much about the defects that may be line defects or even more or grain boundaries and dislocation, so on. But even if we look kind of at perfect systems, they are very challenging to model in conjunction with water. In the end, what it boils down to at the microscopic level is the making and breaking of bonds and chemical reactions, which we want to understand. And as a consequence of this, of course, we get all the structural rearrangement that happen at the interface. I'm using density functional theory modeling, or at least I based all my modeling on density functional theory, which provides us information about the geometric structure, the electronic structure, and also about energetics. And what we want to learn is how the environment, which is determined by its pH, electrode potential, temperature, would influence this solid-liquid interface and the processes that occur at it. Now, the things I would like to touch upon is how do we really study such a solid-liquid interface and understand under potential control and understand how the interplay between the solid-liquid interface and the potential kind of influences what is going on there. I will first talk about how we can realize the potential control in a periodic density functional theory code before turning towards two examples One is concerned with the platinum water interface and has been already touched upon in at least two previous talks, the one by Axel Boos and the one by Jun Chen. And I would like to talk about the impact of water co-absorption on the electrode potential. The second example is from the area of corrosion, and there I would like to discuss how our use of really potential control allowed us to understand the magnesium corrosion and anodic conditions, in particular also the evolution of hydrogen that occurs there, which is a problem that hadn't been understood for a long time. Now with this, since I will be talking about metal-water interfaces, I thought I'll show this picture about the solid-liquid interface, which you've seen already. The double-layer structure has been discussed. And even when we look at the microscopic scale, of course, it is a complicated interface, even if we don't consider all the complication coming from oxide formation and so on. Because we have two condensed phases which come into contact, which have different surface dipole, there will be a potential drop. And of course, when we go towards the bulk of the water, then this potential drop will eventually flatten out. And this region of the double layer is something which would determine in the end the properties of the interface. Because we are dealing with the metal, all of this potential drop is on the water side. If we are dealing with the semiconductor, this picture is a little bit more complicated because then there may be also certain space charge region in the semiconductor. Now, if you want to model something like this in a DFT cell, we want to have an electrode. We would like to have some kind of reference counter electrode, and of course, we would like to have an electrolyte. If we don't have any potential control due to the potential drop at the interface, there will be a dipolar layer of water at the interface, and this will be the potential difference that we measure between the Fermi energy and the metal, and the other side at the reference electrode, let's say, this will be the potential of zero charge. This was also already discussed in several presentations. If we apply a bias or the electrode is charged in some way, then of course there will be rearrangement of the interface to screen the additional charge. So there may be specific adsorption, some ions may be pushed away further from the interface, and the potential will increase. However, if the salt species are able to counteract the charge on the electrode, most of the potential drop is here. Eventually, this won't be the case. So also the ions which are in the solution will start to kind of play a role in screening the potential, because the dipole that is built up here will contribute to the screening, and the potential falls. At some point, there may be barriers may be overcome, and then the potential change will drive electrochemical reactions. And this is something which, of course, we would also like to be able to influence then either increase reaction rate or maybe suppress a reaction. In terms of modeling, what we would like eventually to have is a cell in which, as I said, we have a reference electrode, and this reference electrode is able to basically account for all the excess charge of the non-neutral diffusive layer, but also to be able to allow us to charge the electrode. And how do we do something like this? So what are the design elements? We want an electrified electrode. The reference electrode must be able to donate or accept fractional charges of electrons in order to be able to charge the counter electrode. And we should be able to potentiostat our cell with the help of the reference electrode. Ideally, this will be also only a spectator, so a computational device which allows us to charge our interface and to maintain a constant potential. So it will be something which has a small surface dipole, is inert, to adsorption, reactions, and so on. So really, it's just there to help us control our interface, the interface we are interested in. And so the questions that we need to answer by building up such a electrochemical cell that we want to use in computation is, first of all, how do we kind of get a reference electrode which allow us to charge the counter electrode, the working electrode, and how do we build then a potentiostat? Here is once more in a cartoon way shown what we want to do. So we have our working electrode. In the cases I'm going to show, it is a metal, but in principle there is nothing which stops us from having here also semiconductor. We have a reference electrode which is there in order to exchange charge with the working electrode so that we can reach a situation in which we have a different potential on one side and the other, and basically a potential drop at the interface and electric field running through the cell. Now, the difficulty when it comes to modeling or setting up such a calculation is that typically, this is the supercell I would set up. I have my working electrode, I have water, and I have a counter electrode. But usually we are working with periodic boundary conditions codes. What does it mean? Most of the DFT codes we are using have really periodic repetition of the cells we set up in all three directions. And this means that if I achieve even in my cell kind of this potential drop, so having the working and the counter electrode at different potentials, at the periodic image I have again to have the same kind of potential as on the right on the left side. Fortunately, this is something we know how to deal with because already many years ago, Neugebauer and Scheffler proposed a dipole correction, which allows us to maintain a flat band potential in a vacuum region, and in this way, really achieve the situation that we want to have. There is, however, a second difficulty, and I think this was mentioned earlier in one of the talks, the mandatory condition to have a Fermi level, constant Fermi level throughout the cell. What does this mean? That we may set up our calculation having a working electrode and a reference electrode, for example, both of them metals. We run our self-consistent cycle, and in the end, we end up with one Fermi energy, which effectively removes this potential drop. We realized this early on, and we thought, okay, can't we use a semiconductor counter electrode and use semiconductor concepts to tune the Fermi level? Afterwards, after all, it is the kind of daily business of semiconductor device physics to tune the Fermi level. How does it work? So if I have here a semiconducting reference electrode, I can, for example, we can have p-doping. This would mean because of the equilibration of the Fermi level, there will be an electron transfer from the working electrode to the reference electrode. We will achieve this difference, discharging of the two electrodes. We will have a field throughout the cell, and they will be different potential conditions. What is complicated is what material we should choose. And this was a challenging process. So let us look at what do we want from our reference electrode. Ideally, it will have a very large band gap, and we know that our functionals in DFT underestimate the band gaps. We have also to consider, so the supercell I was showing that both the working electrode and the reference electrode are in one cell, which means that they have to be lattice matched. And if we deform a semiconductor, of course, the band gap will also be usually influenced. So what we want is to have a material which will have an extremely small deformation potential, so that we don't further reduce the band gap as compared to what it is already reduced. We would also like to have a material which ideally straddles the valence and conduction band of water, so that we can access the whole window of water and not have kind of spurious reaction on this side. And as I said, it should be inert to reactions with the solvent molecules. After some search, we came up with a somewhat unusual choice, which was neon. Neon is the material which has the largest band gap of a crystal known in nature. And even in DFT with GGA functional, it is something like 11 eV, which was still big enough for our purposes. Additionally, neon is a van der Waals bonded material, so deformation basically do not influence the band gap. And so we can very easily adapt it in our cell to the geometry that we want, and we still maintain the band gap. And it also is straddling the band gap of water in the way we want it, so that we can really use it. So we have now found an electrode which will allow us to set up such a potentiostat supercell. And here it is once more we put everything together. So we have a working electrode, we have a counter electrode, which is neon. We have the electrolyte sandwich in between. We have a vacuum region in which we apply a dipole correction in order to ensure a flat band potential. And the additional advantage is that we can here immediately read out the applied bias. I haven't said anything about how we do the charging. So we employed the concept of pseudoatoms, which is something that is very often used in semiconductor physics calculations. Probably most of you have heard about pseudohydrogens. So these are objects in which both the valence and the core charge are changed by some charge, so that this is a neutral object, but then we can have charge transfer from one side to the other. All elements in these setups are really very easily to use in a standard DFT code. The advantage is that it works both with semiconductors and metals, and it gives us direct access to the applied bias and the electrode charge. Now, having come up with this setup, we now have to make a potentiostat, which means that we want to maintain a certain applied voltage throughout our calculation. And we have recently developed an ab initio thermopotentiostat, and in this context, I would particularly like to mention Stefan Wippermann and Florian Dyson-Beck, who were instrumental in the development. One thing we have to consider when building up such a potentiostat is that whenever we change the potential of a capacitive system, this is always a dissipative process, which means that if we only adapt the electrode charge to control the voltage, we drain energy from the system. This can be nicely seen here in this plot, which shows the temperature development as a function of the simulation time that we use. Here we used an empirical TIP3P water model. In order to do the simulation, one can see that we basically cool down our system. So we have always to have also fluctuating term, which replenishes the energy within the system in order to avoid this energy, the energy drain. And this allows us then to really maintain the potential, the temperature within the system. So we must be able to basically also potentiostat our system, to thermostat our system via the potentiostat. In order to do this, so the way we control our electrode charge is by, or how we derived the electrode charge control was by using the fluctuation dissipation theorem. So we have a dissipative term, which is a deterministic term. It's equivalent to Ohm's law and dominates far from equilibrium, basically drives our system towards the target potential with a certain relaxation time tau. We have also a fluctuation term, which is a stochastic term. It provides the thermal fluctuations, It is dominant once we are close to the target potential, so the system is close to equilibrium, and it ensures that we correctly sample the thermodynamic equilibrium. We correctly sample the canonical ensemble close to thermodynamic equilibrium. This is a stochastic differential equation, and in order to solve it, Stefan used calculus. I must admit I've never heard about this one before. But in the end, what we end up with is a comparatively simple equation in which all quantities can be easily obtained from density functional theory, and the electrode charge can be directly computed at each MD steps. And also, it is rather simple and can be really easily included in any DFT code capable of molecular dynamic simulations. We have, meanwhile, implementations which are working in VASP and in LEMS, and this is something Florian did, who is a PhD student in Stefan's group. Now, let me now turn towards the application. And the first interface I would like to talk about is the platinum-water interface and the increasing hydrogen coverage. This interface is, this system is a very nice model system. It has some, of course, relevance for industry, which is always nice because of the hydrogen evolution reaction, but because it is also so highly studied, there is a lot of experimental and theoretical work, and it allows us to look really at basic processes there. You have already seen cyclical thermograms throughout this conference. So this is a cyclical thermogram for the platinum water system. And what was our interest? So within this region, you see the potential of zero charge. So basically just the bare platinum surface in contact with water. And along this branch, there is hydrogen absorption. Along this branch, there is hydrogen desorption. And you see that it seems to be extremely reversible. What was also interesting for us, that there seems to be maximum coverage that can be reached with hydrogen absorbs on the surface, which is around 66 monolayers coverage, and afterwards hydrogen evolution starts in. So what we wanted to understand is what determines this maximum coverage. So what leads to this onset of the hydrogen evolution reaction, and why couldn't this be explained in surface science approaches? So basically, if we neglect the water. In order to do this, we performed density functional theory calculations for this interface. We use, for the experts, RPBE functional, which is GGA functional. And we looked, first of all, just at the work function change in vacuum as we put more and more hydrogen on the surface. I would like to point out that our reference here is just the work function of the clean platinum surface also. And what we see is that we follow with our calculated work functions very closely the experimental measurements, and this work function drop is determined, of course, by the surface dipole change at the interface between the electrode and the vacuum region. Now, if one adds water, then something happens. So these are experimental values which were taken, extracted from the work of Markovich. And first of all, we see that we have a very similar kind of dependence on the work function change or electrode potential change with the hydrogen coverage. If we simply shift this curve, you can see that it almost falls on top of the calculations that were performed for vacuum. So this may indicate that water isn't really playing such a big role here. But on the other side, we also see that we don't go quite as far as in vacuum, so we don't seem to be able to reach 1 monolayer. So what is going on? In order to understand this, we now added water to the system and now look at the platinum water interface and add hydrogen to it. In different coverages, this is the green curve, and you can see the coverages we have actually calculated. Let us try to take this a bit apart. So first of all, if we look at the zero coverage case, this should be just the potential of zero charge. So basically we have the rearrangement of the water close to the interface. As more hydrogen is added, there is a change in the potential, so potential drop. And so the hydrogen that is absorbed at the interface seems to be able to screen the charge on the metal electrode, but this works only to a certain region. So at potentials that are going beyond this point, so beyond the coverage of 66 monolayers in experiment, apparently just absorbing hydrogen on the surface is no longer sufficient to screen the potential. And what happens is that hydrogen starts to dissolve, and in this way realizes the screening and can adapt to a higher potential. Indeed, when we look at our calculations at 1 monolayer coverage, we find after about 20 picoseconds that there is a desorption process. So we form here a hydronium ion, and this leads to a tremendous drop in the electrode potential. So this kind of structure seemed to be only metastable, and within the our calculational time, we could see this process for the 1 monolayer cases. We find also rather slow convergence of these structures that we have looked at here. And quite obvious, we do have some kind of change in the behavior within this region. Trying to further understand this, we now decompose the electrode potential into various parts. So the one part is related to the adsorption of hydrogen to the surface. So this is a contribution that we have also in the vacuum. And indeed, if we put this curve on top of the previous curves that we calculated from vacuum, you can see that it kind of nicely follows. When we look about at metal-water interface, however, there are two additional contributions which are contributed to the presence of the water. One of them is related to rearrangements in the electronic charge at the interface. So this would be, for example, the charge transfer from electrons from the specifically adsorbed water molecules, which were mentioned already in Jun Chen's talk. I guess it was yesterday, if I'm not mistaken, but also any kind of polarization effects. And there are effects that are related just to the reorientation of water molecules close to the interface. If you look now at, first of all, this electronic contribution, as a function of the coverage of chemi-soaked water, we see that there is a linear behavior, which indicates that each chemi-soaked water induces an almost constant dipole moment independent of the coverage. We also see that as the hydrogen coverage increases, the number of chemi-soaked water molecules decreases. So if we turn around again to this kind of plot where we plot the electrode potential contribution as a function of coverage, there seems to be kind of a transition. So up to approximately half a monolayer coverage, the two water-related orientations almost cancel each other. So they have opposite contributions and they cancel each other. The only thing that they lead to is a kind of shift of this curve, which we also find from the vacuum. At higher coverages of hydrogen, they no longer cancel each other. So there is a contribution also from the water induced changes in the electrode potential, which are, of course, then reflected in output. So what we can say that at low coverages, the net water impact is small, while at high coverages, the water impact dominates. So it seems that this competition between water co-adsorption and hydrogen co-adsorption is a critical mechanism to understand the electrode potential and the onset of the electrochemical reactions. Because density functional theory, of course, allows us to further analyze the system and look at the electronic structure, this is exactly what we did. And here, what you can see is charge density difference plots for various coverages. And here on the side, we have also taken, so these are two top views, and this is a side view just of the platinum atom from the surface and the water that is sitting exactly on top of it. The conventional picture that we have, so this kind of arrangements has been discussed before, is that there is an interaction between the water 1v1 level and the platinum D states, which leads to the formation of a bonding and an anti-bonding state. And this is a picture that is known from the literature. However, the conventional model assumes that the Fermi energy is below this Fermi energy, between the antibonding state. And so the charge transfer is directly from the water molecule to the platinum atom below it. Now, we looked actually at the charges that we have, and to our astonishment, we found that the platinum atom also loses electrons. So there is not really a charge transfer from the water molecule to the platinum atom directly below it. But what we found that the charge transfer is to neighboring platinum atoms. And this was interesting, also regarding about how many water molecules we can absorb on the surface, because this means that each water molecule requires a bigger surface area than just one platinum atom to absorb. And this reduces the number of absorption sites. We also have to revise our model a little bit, because what happens is that the chemical water molecule anti-bonding level is pinned to the metal's Fermi energy. And this means also that the HOMO of this chemical water molecule is partially occupied and it becomes metallic. And this means that it will have also different properties in terms of screening. So our revised model for the bonding of the chemical water molecule to the platinum surface is that not only the platinum atom directly below the water molecule is interacting and participating in this bonding, but also metal atoms around it. Having discussed this problem, I would like to turn now to a different. This is the corrosion of magnesium. And magnesium is very interesting, also its alloys for structural application, for batteries, but also for medical applications. One of the big problems for magnesium is that it has a very low corrosion resistance. So it is the material that is most susceptible to galvanic corrosion, as can be seen here in this galvanic series. There is also a very peculiar observation regarding the corrosion of magnesium, that there is a really very violent hydrogen evolution at anodic conditions. Anodic condition means that we have positively polarized metal surface, and hydrogen evolution is usually a reaction that is associated with cathodic conditions. But these measurements show that we do have, while initially a decrease in the hydrogen evolution, current density, as we go more anodic, there is a reversal of the behavior. This was first reported more than 150 years ago, but the mechanism wasn't really understood. It has puzzled corrosion scientists for a very long time. This is usually referred to as the anomalous hydrogen evolution or negative difference effect. Now that we can really perform calculations with applied voltage, we thought that this is an interesting system to study, and maybe we can provide some insight. into what is going on. And first of all, we performed calculations under open circuit conditions without applying any voltage, and let the system evolve, looking at what is really going on. And you probably, maybe you saw in the beginning that there was a water molecule. This dissociates, here can be seen again, and hydrogen then penetrates into the surface or moves along the surface. The OH stays on the surface. And if we plot now the trajectories as a function of as they evolve over time, we can see what is going on. So we have blended out here all the magnesium trajectories that correspond just to the atoms moving, as well as the water trajectories of water molecules that are not directly participating in any kind of reactions at the surface, and only leave here explicitly trajectories for water molecules that are involved in what is happening at the surface. We see this water dissociation and the formation of OH and hydrogen. And the hydrogen stays within the magnesium slab, and the OH remains at the surface. We find also a maximum adsorption of a third monolayer of hydrogen on the surface. This is kind of consistent with these fundamental mechanisms that we discussed. Obviously, by absorbing hydrogen on the surface, we can screen, the system is able to screen all the charge on the metal electrode. So if under open circuit conditions, the maximum coverage that can be reached is 1/3 monolayer. And this is also consistent with other studies. Now, if we apply voltage, in principle, what one would expect that this adsorption at the surface will no longer be sufficient to maintain the electrode potential, and so there will be formation of ions within or there will be ions that come into the solution, and we may expect to have some magnesium dissolution. And this is indeed what we can see. So here you can see a molecular dynamics simulation of a magnesium water interface, in which we see that this magnesium atom dissolves from the surface. What was important was kind of that a water molecule sneaks below this magnesium atom, and then it cannot kind of return towards the surface. We also looked at the hydrogen evolution reaction, and here we have blended out all the water molecules that are kind of not interesting, and only left one water molecule which is participating in the reaction in order to show the mechanism. Again, you see here a plot of the trajectories, how they evolve over time. And you can see already that this diagram is much richer than what I showed you for the open circuit conditions. We have again water dissociation initially, and we have hydrogen and OH formation. We also see that some of the hydrogen propagates throughout the water layer in form of hydronium eigen and Sundel ions to go to the other side of the cell in order to screen some of the potential. We also see the onset several hydrogen evolution reactions. So they are shown here in purple. And when we look at more details of the, so here are a few snapshots of the reactions. What we see that there is a water molecule which interacts with the adsorbed hydrogen on the surface and eventually forms an OH and a hydrogen molecule. And this is very reminiscent of the Hirost mechanism, which is the usual mechanism known for cathodic polarization. However, in this mechanism, typically an explicit electron is required in order to drive the reaction, and therefore it was never considered in the studies of the anodic corrosion of magnesium. What we propose is somewhat a modified reaction mechanism, which is based on the observation that the hydrogen atom at the surface is actually negatively charged. And this is a consequence of the high polarizability of the magnesium valence electrons, which lead also in other cases to somewhat peculiar behavior of magnesium. And in this way, what happens is that the hydrogen itself can provide the electron for this reaction, and this is, and then it can kind of happen. With this, I'm already at the end of my presentation and come to the conclusion. So I hope I was able to show you that advancing our methods provide us a new level of realism to describe the double-layer electrochemical processes and provide really very valuable insight into what is happening at these interfaces. In particularly, I looked at platinum water interface and the co-adsorption of hydrogen, and discussed the limitations which we have in the surface science approach due to the neglect of water. Was hopefully able to convince you that we have an idea of the origin of this maximum adsorbate coverage that can be reached for the hydrogen, which is connected to the onset of the hydrogen evolution reaction and the origin of the overpotential. And we propose a revised picture for the metal hydrogen bond within this system. In the end, I discussed the atomistic mechanism leading to the anomalous hydrogen evolution on magnesium, and also showed you that we can really start to look at dissolution processes as we drive the system, if we can potentially control the system. And all this work is can be found in these 3 papers. And before I finish, I would really like to acknowledge my collaborators, in particular Sudarshan Surendranal, who was a PhD student and is now a postdoc in my group and who performed all the work on platinum and magnesium. Stefan and Florian I already mentioned, and Christoph Reisold was, of course, also involved on the work and the thermopotentiostat. Mike Finnis was involved in the work on the magnesium corrosion. And last but not least, I would particularly like to acknowledge Jörg Neugebauer for continuous support and always very insightful and helpful discussions. And with this, I'll thank you for your attention. I'll be happy to take questions.
Thank you very much, Mira. So that was a very nice talk, and we already have some questions here. Let me see. So the first one comes from Babu. Perhaps we can. Okay, you should now be able to ask your question.
Hello.
Yes, we can hear you. Yes.
Yeah. Okay. Yeah. First of all, thank you for the nice talk. I just have a very fundamental question. I mean, when you were explaining about the p-type doping of the reference electrode, so if I understand, the p-type doping simply means the depletion of electrons, right? So yeah. Maybe you can explain it one more time again if I missed something, I guess.
Yes. So basically, we realize p or n-type doping by controlling the charge on the neon. So I talked about this pseudo atoms. So we have pseudo neon atoms. So if we want to have a p-typed dope a neon electrode, so let me try not to get it wrong. We have to have a neon in which we, I think we add a little bit additional charge. So this is then the other way around. We have to remove some charge so that we get charge transfer from the metal electrode to the neon to the neon electrode. So we basically control the doping and make it p or n-type doping by controlling the pseudo charge on the neon.
So if I understand, I mean, so the charge should be transferred from the metal to the neon atoms.
Yeah, so let me see if I can go to the picture where I have
this looks like the neon atom will gain the excess electrons, so it should look like n-type doping.
So So if the neon gets yes, then it's n-type doping, then p-type. I have to think always in which direction I put it, but basically we really change the charge on the neon. Sorry. Here.
Okay, yes, I hear.
Okay, so we change the, so we need to take care of, we change the valence charge basically. Of course, if we have a pseudoatom, this also changes the charge. We have to change also the core charge. So we have a neutral object, and this is very important that we really have a neutral object, because then even if we have different charges on the neon, so on the reference electrode and the working electrode, our overall cell is neutral. So we don't have anything like background charge or something in order to, we don't deal with a charged cell.
Okay, yeah, thank you.
Okay.
Okay, so this was also not clear for me. So in the neon, you both subtract this Q from the core, from the pseudocore, if you want, and from the number of electrodes, of electrons. Okay.
So you probably, I mean, you've heard probably, or you've used pseudo-hydrogens. Usually we don't think really what they are, but they're an object which have, for example, 3/4 charge on the core and 3/4 charge on the valence, and they're used, let's say, to saturate dangling bonds. But here we kind of misuse this concept, if you wish, in order to do the charging in the cell.
I see. Okay, very good. So then there is Deepak Kumar who would like to ask a question. Deepak, are you there?
Yeah. Nice presentation. So I'm curious, like.
Hello, we cannot hear you well, or at least I cannot hear you well.
During your simulation.
Sorry, I didn't get this.
Deepak, for some reason we hear you very strangely. Perhaps I can just read the question.
Oh, okay.
It's kindly comment on the number of interfacial atoms or molecules considered during your simulations.
Okay. So, I mean, in the calculations with both platinum and magnesium, when we were looking at the flat surfaces, we had like 64 water molecules. We had, I think, like always 4 layers of metal. And we had, for platinum, for sure, 4. In magnesium, I'm not sure whether we used, in some cases, also 3 layer, but we tested this very careful. And then we had the neon layer, which basically had always the same number of atoms as in the first metal layer. For the simulations in which we had, I was showing the dissolution, we had a vicinal surface, and I think the water molecules were more than 100. I don't know the exact number, I will have to check. But we always very carefully test also the convergence with respect to cell size to make sure that we kind of can make the conclusions that we give.
Okay. One thing which I would like to know is, in your calculations, kind of, are the usual standard functionals good enough, or did you experience any issues with the?
Yes, there are there are issues. So I mentioned that for the platinum water interface, we used the RPBE, and this was necessary because the PBE was not good enough. And the reason is simply that, I mean, we know that we underestimate the band gap of water severely. And in most cases, this seems to work if we use GGA, because the water stability region, so this was discussed already with the redox levels, is basically just within the band gap of water. Now, what happens in the platinum water system is that the Fermi energy of the platinum is very close to the valence band maximum of water. And as we run DMD, then what can happen is that there is kind of charge sloshing in between these 2 levels, and the calculation crashed. The solution with RPBE was that RPBE describes the the Fermi level, so the work function of water a little bit, of platinum a little bit worse than PBE compared to experiment. But it also allowed us, by using RPBE and van der Waals, to go to somewhat lower temperatures. So Axel has a paper in which he discusses all the functionals, and I guess there they made a recommendation for also describing water to use RPBE and van der Waals, which gives you also a nice description of the water. So this was our kind of, reason to use RPBE in the platinum system. This is still not very good. I mean, we have to use hybrid functionals if we want to describe the water band gap somewhat correctly. And this has, if we are looking sometimes at charge transfer reactions, this may become an issue. For example, for the if you look just at a chlorine ion in water, then you have to use hybrid functional if you want to describe, for example, a transition between a neutral and a charged chlorine ion. But we know also that hybrids are not really a good choice when we are thinking about metals. So, and also when we think about semiconductor water interfaces, we may use kind of a different screening parameter in order, or may need to use a different alpha parameter in order to describe both the band gap of the semiconductor and of water correctly. So I don't have a good answer there. I think this is something we have to work on and really see whether there is some, I don't know, some molecular U or something which will allow us to do these calculations. But yeah, we have to be just very careful of what we do.
Okay, thank you very much. Are there any further questions? I cannot see any raised hands or questions. So if not, then thank you very much, Mira, again. And thank all of you who have contributed to this workshop with very nice talks and so on. And one very important thing which I would like to do before asking the fellow co-organizers for some words of conclusion is that I would really like to thank all the people who behind the scenes have helped make this workshop successful. So most of all, it's obviously Monica, Victoria, and Adriana, who in the secretariat of the workshop made all these things which are invisible to us while we give the workshop, but thanks to them, really, this was could run very smoothly. Also, my colleagues from the ICTS, so the computer section, Massimo and Walter and so on, who all the time are there, and when Zoom crashes or so, they are always with a hand on the mouse to click on the right button. So all these people who we did not see and who did not talk during the workshop, but they made a very good job allowing us to have this quite smoothly. Okay, apart from these thanks, Nicola, Simone, Laure, do you want to say something more?
Maybe I will just add a couple of words.
Yes.
So to thank all the speakers and all the participants who contributed to the discussion. And among the 4 organizers, I was the most skeptical in organizing this meeting as a virtual meeting. And but my fellow co-organizers were convinced that this was indeed a good idea, and I completely changed my mind. And so I thank you all for convincing me that this was a good idea, and indeed it was. So yeah, thanks again to all the people who contributed, and yeah, see you next time.
Well, what can I say apart from thank you again? And I think we have plenty of food for thought now of how little we understand and how we are progressing, but how many open questions there still are. And yes, so thank you very much to everybody, and hope to see you soon.
Yes, thank you also from my side, and I hope really to have the next conference in presence, in addition to the virtual editions, and then to meet you all again in Trieste.
Yes, drinking espressos and so on. Yeah, I think really one thing which one or two things which really this week has shown abundantly clear, both in experimental and in theoretical talks, is that this is a very relevant topic for the future, for the near and further future, because the energy topic and the way of how to store energy in chemical bonds, this will have to pass through electrochemistry somehow. And so I think it was very clear this week that this is all very important. And the other thing is, which was also clear, is that neither from the theory side nor from the experimental side, we already know enough. I mean, there is still a space for a lot of research to understand better these phenomena. And because of this, because of the importance, because of all the unknowns, I'm sure that this community here is not the last time that we all are meeting each other and discussing science. Okay, so if there are no other comments from anyone wants to say something? No? Okay, then I thank also all the participants.
Maybe
yes, sure, Mira.
Thank you very much for this really wonderful workshop. It was so nice, and for putting it together, and really it's one of the very nice virtual workshops I've participated in. And yeah, thank you again. So really.
Thank you. I'm happy. We are happy if this is perceived as something useful. Okay, so I wish all of you a very nice weekend, and I'm sure we will all meet soon again. And thank you also to all the participants who invisibly are behind the scenes listening, and for the people who watch the streaming and so on. Okay, thank you very much.
Thank you.
And goodbye.
Bye-bye. Bye-bye.
Goodbye.